Okay, we have here a DC power supply, which will result in a constant current through the solenoid, which will produce a constant magnetic flux. So we have a constant current through the solenoid, so the flux linkage of this coil is also constant. So everything is very peaceful until the arrival of the iron rod. When the iron rod is in the coil, the magnetic flux density in the coil is going to increase. There are two ways to explain this. The first way is the magnetic flux density in the coil is dependent on the magnetic permeability of the medium in the coil. Some of you may actually know the formula for the magnetic field created by a solenoid. It's given by mu and I, and this term here, mu, is the magnetic permeability of the medium. The magnetic permeability of iron is much higher than the magnetic permeability of air. So when the iron is in the coil, the permeability of the medium in the coil will be much higher, and this will give a boost to the magnetic flux density within the coil. So this is the first way to explain. The second way to explain this is to realize that iron is magnetizable. So when the iron is in the solenoid, the iron itself gets magnetized, and it will be magnetized in the same direction as the magnetic field of this solenoid. So let's suppose that the magnetic field of this solenoid is say leftward. So when the iron is moved through the coil, whenever the iron is inside, it gets magnetized and it produces its own magnetic field, which is in the same direction as the solenoid's magnetic field. And so whenever the iron is in the coil, it gives an extra boost to the original magnetic field that was created by the solenoid. So either way you see it, what's going to happen is when the iron enters the solenoid, the magnetic flux linkage of the coil is going to increase. And this increased magnetic flux linkage will drop back to the original value only when the iron rod is moved out of the solenoid. That means the magnetic flux linkage of this solenoid is going to increase as the iron rod is moved in, and is going to decrease as the iron rod is being moved out of the solenoid. Faraday's law says that the induced EMF is given by the negative of d phi dt. So when we have this positive gradient here, we are going to have a negative induced EMF. There's no induced EMF here because there's no change in the magnetic flux linkage. What we have here is a negative gradient. So with the negative sign here, the induced EMF is going to be positive here. Let's go back to our circuit here. So we have a constant DC power supply with a EMF, let's say E. So as the iron rod is being pushed in, we actually have an induced EMF in the coil that's in the opposite direction to the power supply's EMF. So during this stage here, the current is going to dip. During this stage here, there's no induced EMF, so the EMF of this circuit is back to the EMF of the battery, and so you go back to the original current. At this point here, you have the induced EMF again, but this time the induced EMF is in the same direction as the EMF of the battery. So you're going to have a spike in current here. So this is how the current is going to vary. Actually, it's possible for you to arrive at this answer directly by just applying Lenz's law. So as the iron rod is moved in, the change is actually an increase in the magnetic flux linkage. So Lenz's law says that the induced EMF will produce an induced current whose magnetic flux is to oppose the change So the change is the increase in magnetic flux. So to oppose the increase, the induced current must try to decrease the magnetic flux in this coil. To decrease the magnetic flux linkage, the result must be an induced current that's against the original current in the solenoid. So you know the current must dip first. On the other hand, when the iron rod is leaving, the change is actually a decrease in magnetic flux linkage. So the induced current must be such as to try to increase the magnetic flux linkage. So to increase the magnetic flux linkage, the induced current surely will flow in the same direction as the original current in the solenoid. That's why it's a spike here. Okay, that's it. Ta-ta!